The Rockies are right over there. Don't just go to the conference. Go and see the Rocky Mountain National Park. Go hiking up at Bear Lake or something. Don't do what I did, which is just to come for the conference. Go and see the area.
Good afternoon. Together, let's build a single producer, single consumer, lock-free FIFO from the ground up. My name is Charlie Frasch. The cover slide says Charles. My name tag says Charles. You can call me Charlie. I'm a senior core developer at the IEX group, and I've been writing C++ in high performance software and trading software for about 20 years. Little story about IEX group. If you're in the industry, you know then that the IEX is the hero of Michael Lewis's Flash Boys. Well, I worked for Thesis Technologies before I worked for IEX, and if you knew some of the names in there, one of the arch villains in that novel was Thesis Technologies president. Find his name in the very end of the book. Anyways, we're going to be looking at a lot of pretty close to be compilable slideware, but it's slideware nonetheless. You can find the real source code for the examples that we're going to go through on my GitHub account. There's the URL. I want to caution you that the code is kind of C++23 as implemented by GCC 12, so there's some stuff that's not there. And I do have to tell you that the views I express here are my own and may not reflect the views of the IEX group. So I hope to not have too many opinions, so that shouldn't be an issue. So why another single producer, single consumer FIFO, and we can get them from reliable sources like Boost.Lockfree? Well, it's fun, right? So writing such a FIFO by yourself is a pretty gentle introduction to lock-free programming. And there's some pretty interesting performance optimizations that you can make that in some cases don't show up in the out-of-the-box ones. And finally, you may have some specific requirements that aren't met by out-of-the-box implementations. And if we haven't, I hope we have enough time to get to the example that I'm going to show you. At the bottom, I've listed a few sources, and I want to point out in particular the 1024 cores URL. That's Dmitry Vyukov's pages. It's just filled with all kinds of everything lock-free and all kinds of different FIFOs and other things as well. So when I say single producer, single consumer, lock-free, wait-free FIFO, what do I mean? Well, the single producer part, it means there's just one producer or thread, and if more than one thread tries to write push data onto the FIFO, then it's undefined behavior. Likewise, a single consumer means there's exactly one consumer reading values out of, or popping them out of the FIFO. And again, if there's more than one of those, the behavior is undefined. The lock-free part means to me that it doesn't use mutex locks. There's other definitions for what lock-free means that computer scientists know stuff about. I'm not a computer scientist, I'm a practitioner. The wait-free part is a further improvement, more or less, to the lock-free part, and it means that each thread moves forward regardless of how the other threads move. And the FIFO part is, well, I call it a FIFO because that's what we call it at the place where I work. But you might call it a circular FIFO or a circular queue or just a plain old linear queue. That would all work. Single fixed size buffer used as if it were connected end to end, such that the oldest entry is processed first. So what do we use SPSC FIFOs for, especially in my industry? Well, here's an example. You create a pipeline of processes. Suppose you have one thread reading from sockets, another thread that handles the messages that come in on those sockets and maybe produces the result, and a third thread that maybe writes a response to the network. Those can be connected by single producer, single consumer FIFOs. And there's a couple advantages of that for this. It may improve, of course, all these advantages and disadvantages are subject to measurement, always measure. It may improve the throughput over just a single thread doing all three of those operations. In fact, I'd be surprised if it didn't. It also should improve the resiliency of the application to spikes in message traffic. Some of the disadvantages are, well, you have to manage 3 threads. It probably uses more memory because each of the FIFOs needs a place to store its messages. So everybody here should be a computer programmer. So you should be familiar with circular FIFOs, circular queues, but let's go through that anyways. Here we have a circular FIFO with 2 cursors. The push cursor is on the outside. Things get written at the push cursor. The pop cursor is on the inside. Things get read from the location of the pop cursor. Right now, the FIFO is empty. And at the bottom, you can see that circular FIFO unrolled to show how it appears in memory. And so when we push something onto the FIFO, it gets copied into the FIFO, and the push cursor is incremented. Now, the push cursor and the pop cursor are no longer equal, so the FIFO is not empty. Push another value in, same thing happens. Eventually, we push enough values in, the FIFO fills up. At the bottom, in the linear representation, you can see that the push cursor is capacity greater than the pop cursor. In this case, it's 8, so if you count all those little squares over there, after you count to 8, you'll reach the push cursor. So this says something about this representation says something about how I'm going to use cursors in the examples that I show. There are different ways to do this. The way I'm going to do it is use 64-bit unsigned integers, so there's lots and lots of numbers available for use. And we're going to start at 0, and every time we do a push, we increment, and probably you won't run out of them, especially if you have a system that reboots periodically, like once a day, once a week, has a maintenance period or something like that. And of course, we're going to do the same thing for the pop cursor. Now, alternatives are restricting the capacity to integral power of 2 and using AND operations to convert the, that's not right. I lost my train of thought. So we do have to convert that continuously increasing cursor value to an offset in an array. And I'm going to do that using the remainder operator. That's a slow operation, but it's easy to type. It's easy to do on slideware. The two alternatives that I know of is to constrain the cursor to the allowable range of indices on the array that's storing the values. That has some advantages and disadvantages. Its advantage, of course, over the remainder operator is that there's no division in it. Remember, division, 20, 30 cycles, adds, I don't know, 1 or 2 cycles. And the other way you can do it is constrain the size of the capacity of the FIFO to an integral power of 2 and use the AND operator with 1 minus the capacity. That's a 1-cycle operation. And I'll try to show that the difference in performance at the very end of the presentation. So the push is kind of the opposite. When you pop a value, you remove it from the location where the pop cursor points to and increment the pop cursor. Want to pop another value, do that, and eventually you've popped all. If no new values get pushed on, eventually the pop cursor becomes equal to the push cursor, and again, our FIFO becomes empty. So this, and the next slide, implement that functionality. So in FIFO 1, it's a template parameter. It takes a T, which is the value that we're going to store in the FIFO, and an allocator type. We have 4 member variables: the capacity, a pointer to the first element that's allocated by our allocator, and our push and our pop cursor. And when the constructor takes the capacity and an allocator, which defaults to the std allocator that's supplied in the default template parameter, and of course we store all that stuff, and then we allocate capacity. We allocate our ring buffer. Now remember what allocate does. That allocation allocates capacity, size of T times capacity, number of bytes, as if the global new operator were used. Then it starts the lifetime in an array of T in that storage location, but it doesn't start the lifetime of any T's. So that'll become important later on. Skipping the destructor, we have a couple of accessors that, like you always have in container-like things, and then so the push operation is implemented like this: in comes the value by constref. Now, I'm not doing a lot of extra work on the interface here, so we don't have specializations for R value reference, R values and stuff like that. But if you want to write one according to your requirements, needs, you can add that kind of stuff. So we take a value by constref. If the FIFO is full, we immediately return false. Otherwise, we copy construct the value in our ring and increment the push cursor and return true. So notice there's no loops in there. There's no atomic compare and sets. It goes through in a finite number of steps, more or less, and immediately returns. This is what gives us the weight freedom, at least for the push operations. And the pop operations are very similar. Of course, this time we pass in the value by reference and check if the FIFO is empty. If there is, there's nothing to do, and we return false. Otherwise, we copy construct the value in the ring at the pop cursor into the variable that was passed in, destroy the instance that was in the pop cursor, and increment in the ring at the pop cursor, and increment the pop cursor. So we do that for a couple of reasons. Even though objects go out of existence, one of the ways objects go out of existence is when their storage is reused, which of course when the FIFO works its way around, we'll reuse the storage again. But some applications rely on the side effects of the destructor, so we'll just do that. It doesn't. For all examples, all performance examples, is there a question back?
Yes. Don't you need here move std move on the value?
You could do that. You'd have to use a different constructor probably. I don't know. This works. This works for my purpose. Like I said, you can fiddle around with these things any way you want to, because it's open source, and it's, yeah, you can do that. So where were we at? So we're all good computer programmers here, good and professional computer programmers. We compile a unit test. We include all the recommended warnings, W-error, W-all, W-extra, W-conversion. We include the address sanitizer and the undefined behavior sanitizer. We run it, all unit tests pass. We also write a little performance program application. What the performance application that these show are, they push a number of values onto the FIFO in one thread and read that same number of values off the FIFO in another thread, verify that the value that was pushed in is the value that was popped, and if they differ, it throws an exception. So we didn't get an exception, otherwise it would have printed out. So, and we get, I don't know, 7.5 million or so operations per second in debug mode. So we're happy with this. We go ahead and compile in release mode, and we run it, and bang, something bad happens. What happened? Well, we'll find out in a minute, but you can see that, well, after you read the code on my GitHub site, you can see that what happened was that the value that was read in the pop thread was not the expected value. So it threw the exception. So what do? Since we have a multi-threaded program and there's one more sanitizer, the thread sanitizer, let's go ahead and recompile with the thread sanitizer and run it. And well, our suspicions were confirmed. There's a data race. In fact, if you read the mess that the thread sanitizer puts out, there's 4 of them, or you do some analysis. No, there's 4 data races in this program. What are data races? Well, CPP reference and the spec says it basically says if 2 threads, if there's a read and a write, and well, I'll just read it to you. When an evaluation of an expression writes to a memory location and another evaluation reads or modifies the same memory location, the expressions are said to conflict. And if there are 2 conflicting evaluations, a data race happens, unless both evaluations execute in the same thread, which is not what happens here, or both conflicting evaluations are atomic operations, which doesn't happen here, or one of the conflicting evaluations happens before the other, and you can follow that link there and get the complicated definition of what happens before. And we'll just kind of dive into that just a little bit. If none of those 3 conditions are met, we have a data race. If we have a data race, we have undefined behavior. And if you went to Fedor's talk this morning, he should have convinced you that you don't want undefined behavior. And in fact, this is an example where we have undefined behavior and we don't get the expected result. So we can, to help reason about what's going on in these 2 threads, we can create timelines that show the order of the evaluations that occur in both threads. So on the left-hand side, the push, the right-hand side is the pop. And starting at the top, we see that we load the pop cursor, that's okay, but we load the push cursor, that's okay, because the push cursor, the only place the push cursor is stored is in the push thread, but the pop cursor is stored in the push thread and stored in the pop thread and loaded in the push thread, and so those are conflicting evaluations, and so that's a data race. And if you look in the pop thread, kind of the same thing happens with the pop cursor. The push cursor is stored in the push thread and loaded in the pop thread. That's data race number 2. On the next line down is where we're doing that copy construction into the ring. So we're storing in one thread, loading in another thread. That's the 3rd data race. And it turns out that there's actually 2 data races associated with that. store in one and load in the other, and I hope we'll see that a little farther on. So the push. So to cure the data, the easiest way to cure the data races between the cursors is to make those atomic, and that automatically cures 2 of the 4 data races. The other data race is a little more complicated. When we store the value in the ring, we're doing that in a constructor, and generally complex operations like object construction are difficult to make lock-free without using mutexes. But if we used mutexes, we wouldn't have a lock-free FIFO anymore. So the tool that we have left is to use atomic operations to create a happens before relationship between the store and the push thread and the load and the pop thread. And so we modify FIFO 1 and it becomes FIFO 2 by changing the type of the push cursor and the pop cursor. So stood atomic is the library that's, is available, and it performs that function. But one of the other things we can do is now we can assert that our FIFO, we can add a static assertion that'll trigger if our atomic variables are not always lock-free. And this is important because the standard doesn't require lock freedom for every type. There's only actually 1 or 2 types that the standard requires to be lock-free. But all quality implementations, atomic operations on intrinsic built-in types like in 64-bit integers are in fact lock-free. But you don't want to find that out, midnight when your high-frequency trading application crashes. You want to find it out at compile time. So here's what our timelines look like after we make the cursors atomic. So notice that we didn't change we didn't change push or pop operations themselves. We just changed the type of the cursors. So what that means is that every operation, all the built-in operations on the atomic type carry with them what's called sequentially consistent memory ordering. And that gives us a couple of good things. So if we look at the push cursor increment, when the increment is completed, the push cursor gets stored. The store operation with sequentially consistent ordering constraints creates what's called a release operation. Over on the pop thread, when we load the push cursor, that creates an acquire operation. So the combination of the release and acquire on the same atomic variable creates what's called means that the push cursor store is sequenced before the push cursor acquire in the pop thread. That does a couple of things. In addition, so that sequence before thing assures that none of the operations that occur in program order before the push cursor get reordered by either the compiler or the processor. And the same thing happens over on the pop thread side. None of those evaluations that occur after the push cursor load can be reordered to occur before the before the push cursor load. So the combination sequenced before relationship between the store of the push cursor and the load of the push cursor creates the happens before relationship that's needed to meet one of the exceptions to the data race language in the specification. So what it means is that every operation in the push thread that occurs, and this is every operation, not just atomic operations, every operation that occurs in the push thread before the release operation becomes a visible side effect, it's on the other side, a visible side effect in the pop thread. And that cures the third data race. And the last data race is a little harder, especially for me to understand. But we have to make sure that the pop thread is finished loading the value before the push thread takes another whack at storing the value. And so again, the same thing, the same happens before relationship is created when the pop cursor is incremented and the push thread reads loads the pop cursor as part of determining whether or not the FIFO is full. Is there any questions? I'm sure there are. Okay. So we compile that program. We compile our unit tests. They all pass. We compile this time with the thread sanitizer and get a clean bill of health. We run our performance benchmark in release mode, and we get 13 million operations per second, if you believe my benchmark. And you can code review it on my GitHub. In fact, I'll warn you right now, there's undefined behavior in it, but for some reason I can't get GitHub to refresh on my machine, so I can't fix it. I'll have to fix it when I get back to Charleston. But we can do better. Remember I said that default operations on atomic variables carry the consistent, what's it called? I hate that when that happens. It's sequentially consistent memory ordering. And that has, in addition to the release acquire semantics that you can get from that, there's a whole bunch of other ones that you can find out about by reading CPP reference. It's probably a little bit easier than reading the spec. But there's also another thing that it does. It provides a total ordering in the entire program in the order in which atomic variables are read. We don't need that. We only need the release acquire semantics that the sequentially consistent ordering gives us. And there's actually something else that's maybe even more important, and that's we need to avoid false sharing. So if you had eagle eyes, you would have noticed that the push cursor and the pop cursor were declared in the FIFO1 class right next to each other. So chances are those variables resided on the same cache line. Now you'll recall that especially all modern processors use some sort of caching to improve the performance because it's a long haul between the memory and the processing core. So they reduce that by creating cache lines. Our cache lines on the Intel are 64 bytes, and there's usually separate caches for each core. So these performance benchmarks will run on a multi-core machine with the read thread and the write thread pinned to different cores. So there were, of course, concurrent, if you store a memory variable, it has to eventually show up in other cores that want to read that same virtual address. Anyways, we can fix the we can fix that by aligning our cursors. And we spell that by as STUD hardware destructive interference size, which is the C++20 feature that evaluate, and it's just a constant, and it evaluates to 64, which puts each cursor on its very own cache line. We also add some padding after the pop cursor to ensure there's not some accidental false sharing by something that happens to show up, say on the stack, if you have it on the stack or in a larger class, on the same cache line as the pop cursor. I've added also a couple of helper functions to help decide whether our FIFO is full, empty, and how to compute the element. You can see there where I use the remainder operator. And notice that those use the raw values. They don't use the atomic values. And so we don't have to deal with the possible slowness of some of the atomic operations. But the other area that we want to exploit is getting rid of these sequentially consistent memory orderings and just using the plain old ordinary, using the release and acquire ordering. And we can do that because almost all the member functions on the atomic types also carry memory ordering parameter, and it defaults to sequentially consistent. But if you supply it, of course, it gives you the value that you supply. So we've changed both the push and the pop operation. And the way this works is we can load the push cursor using what's called memory order relax. And because the push cursor is only stored in the push thread, we can do that. And what it means is that it's basically just a plain old ordinary load, but it's an atomic load. It doesn't carry any memory consistency things with it at all. Pop cursor, on the other hand, we saw from the other diagram that when we loaded the pop cursor to decide whether the FIFO was full, we wanted that load operation to carry an acquire constraint. And now we can use now that we have those as plain old ordinary variable 64-bit integers, we can use our full helper function to decide whether the FIFO is full. If it is, we return false. Otherwise, we do the same thing, except instead of using the prefix increment operator, we store whatever value the push cursor has now incremented by 1. And remember from the previous diagrams, we wanted that push cursor store to carry the release operation. And the same kind of stuff happens in the pop thread. We go ahead and compile that, all test pass. The thread sanitizer says things are great. We run it, performance benchmark and release load, and holy cow, 50 million operations per second, about a 4x-ish improvement. And so I urge, if you're at all interested in doing this type of stuff, it's worthwhile fiddling around with that. It would be worthwhile fiddling around with that FIFO 2 and try and see what the different effects are between the false sharing and not false sharing, and relaxed atomics versus not relaxed atomics. I don't have those numbers here. I have to confess that I have not done that, but I'm going to when I get back to Charleston. Now we're going to take a look at an optimization that I found on Eric Rigtorp's blog, website, and GitHub page. And you can find that also on the last page of the presentation, where there's a bunch of other references that have, I think, useful information. And so what the idea here is that unless the FIFO is full, we don't, in the push thread, we don't really need to actually read the real current value of the pop thread, so we can cache it. And you can make the same statement, a similar statement on the pop thread. The only time we really care about knowing the exact value of the push thread is when we're trying to when the FIFO is empty. So we create. Notice that we create two more aligned cursors. These are not atomic variables because they don't need to be. They're loaded and stored by their own thread. So the push thread loads and stores the cached pop cursor, and the pop thread loads and stores the cached push cursor. So no atomic operations are needed there. But we do need to revise our push and pop operations a little bit. The way it works is that, of course, those cursors were all initialized to 0 when the FIFO was created. So when we want to push a value, we get our push cursor and we compare it with the cached pop cursor. If it's not full, we continue with the rest of the operation. But if it is full, we go ahead and load the pop cursor again using the memory order acquire operations and store it in the cache pop cursor value and recompute whether the FIFO is full. If it's full this time, then we just return false. Otherwise, we continue with our operations. Our push operations. And we do the same kind of calculation on for the pop, except, of course, the cursors are different. And again, we compile all unit tests pass. The thread sanitizer says things are peachy here. We run it in our benchmark and release nodes, and holy cow, amazing 165 million about operations per second, if you believe my benchmark. Compare that with, it's what? That's a 3.5x over the FIFO 3, and I can't multiply that big of a number for the FIFO 2. So now, yeah, we have enough time for this. Now imagine, remember that pipeline diagram I showed at the beginning of the presentation. Let's simplify that a little bit. And suppose we have some type foo that we need to pass around over the network. And so we have a thread called read and push foo that reads those foos off the network and pushes them on the FIFO, and another thread that reads those foos off the FIFO, does some computations, and pushes them back onto the network. So we have our foo at the top. It's got a couple variables that we'll use in this example. We also want it to be, in this particular case, implicit lifetime, which will allow us to do legally. So if you were at Fedor's talk this morning, he talked about how things are getting better in stuff like reinterpret casting that have been traditional ways of doing things, like reading bytes from sockets and turning them into classes. Well, we all know that unless there's an actual object there, at least before C++23, unless there's an actual object in that buffer of bytes, that reinterpret cast is undefined behavior. So the implicit lifetime change in C++23 remedied some of that. So on our read and push foo operation, we prepare a buffer of sufficient size to hold a foo, and it is properly aligned for whatever foo's alignment is. And we use that buffer as the target for a read, system read operation. And the idea here is that we're reading the object representation of the foo into the buffer. And then the implicit lifetime changes to C++23 allow us to use this start lifetime as foo in place of reinterpret cast. And so we can convert that buffer, since we need to know a priori that that buffer has bytes for a foo in it. But if we can get around that problem, we can start the lifetime as a foo. We get back a pointer to foo. Now, what we want to do is check whether foo bar has some particular value. If it doesn't, then we throw an exception. And if we don't throw the exception, we push that foo onto the FIFO. The other thread pops it off. It pops that value, that foo value, into our foo variable. It does some processing on it, for example, set the value of blat, and then forwards that onto somewhere else in the network. But the key point of all this is that took no less than 4 mem copies, and the lines where they happen are annotated on here. And in my experience, and yours too probably, you know that memcopy for pretty big things like, say, 100-byte structures it takes a long time. And in fact, in my experience, it dominates the operations on any kind of FIFO. So we want to strive to remove as many of those as we possibly can. So suppose we could do something like this. Suppose we could create some kind of smart pointer-like object, and it's called pusher here. And we use the get operation on that pusher to get at the memory inside the FIFO at the push cursor. And we use that as the place where the socket read is going to deposit all its bytes. And then when we come back from that, we can test since this pusher variable is a smart pointer, we can dereference the bar and test its value. And if it's not the value we expect, we'll still throw the exception, but we want to release that pusher beforehand, because at that last curly, when the read and push FIFO returns, the destructor of our pusher is going to want to advance the push cursor. And on the pop, we do the same thing. We create a smart pointer from the FIFO that points to the element in the FIFO where the pop cursor points. We check that value, and if it doesn't evaluate if it evaluates as false, then that means the FIFO is full and FIFO is empty and we don't need to do anything. Otherwise, it'll return true, and we can do our operations on it by dereferencing the smart pointer, and then again get that address that it refers to and use that as the source of bytes for the write operation. And we can reduce the number of mem copies by half, which can result in substantial performance improvements. So I'm going to run through this real quick on how we do that. So we have a factory operation called push with no parameters, and we have another factory operation called pop. So the pusher is kind of a really stupid little smart pointer proxy type of an object that holds a pointer to our FIFO and the value of the push cursor. When it goes out of scope, if FIFO is still not null, it advances the push cursor, and then again we can also evaluate. It evaluates either true or false based on the value based on whether or not FIFO holds a value, and we have that release operation that sets the FIFO pointer to null, and then our smart pointer operations where we can get to the different value, different things inside in the FIFO at the push cursor location. And so to use that, It's pretty straightforward. We use the same kind of calculations in the factory function as we did for push, except instead of actually copying at this point, we create our pusher. If the FIFO is full, we create it by the default constructor, which leaves the pointer null. Otherwise, we convert it with a pointer to ourselves and the value of the push cursor. And then we can rewrite push in terms of our pusher. We can do the same thing. We can do the same thing for pop. And again, we can do our unit tests, thread sanitizer, and perf. And it turns out, as you would expect, since it's basically the same as FIFO 4 with some extra gloss added, its performance is about the same. It's a little bit less, maybe, because of the branch and the destructor and the need to look at that variable. But there, 65 million is approximately 65 million, regardless of all the least lesser significant digits. All right, so what did we see here? Those benchmarks were run on my desktop computer. It's an 8-core, 3 gigahertz machine, run Ubuntu 22 under Windows subsystem for Linux 2, which means it's virtual machines. We used 2 to the 17th FIFO size, transferred 64-bit integers, did 100 runs of each one of the performance things. Each run was 400 million iterations. And from those 100 runs, I computed minimum, maximum, median, and mean values for those. So FIFO 2 and the mutex were so slow, I didn't run that much, but we already knew that those were not really, well, we knew that FIFO 2 is not a viable one to use. So the FIFO 3, it used relaxed atomics and no false sharing. FIFO 4, remember, we added cache cursors. Number 5, proxies, so those two are the same. Now, Boost is Boost.Lockfree, SPSC, specialized for fixed size. That 2 to the 17th is the size I used. It's a little bit slower than our FIFO 4, and I really didn't have a good explanation for that. I think it's because, so the Boost version that I used was, I think, the latest one that they have, and they did some work on that, and they pass these functors around to do the value copying, and my suspicion is that G++12 with 03 can't quite see through those functors. I don't know what it is. But we'll also, in the next slide, I'll show another comparison. So the RigTorp is that Eric Rigtorp's cache cursor FIFO that I mentioned earlier in the presentation, and he's a lot faster than any of our other FIFOs. And the reason for that is he doesn't use remainder. He uses a scheme where he adds an extra element in the storage array that he uses as a sentinel so that he can distinguish between a full FIFO and an empty FIFO. The last one is uses mutexes, and it's just there for kind of performance, but it's not lock-free, and it's also not single producer. You can have as many producers and as many consumers as you want. So I did a little experimentation with FIFO, not only with FIFO 4, to change it to that AND operation on by constraining the capacity size to an integral power of 2 and using the AND operations to compute the index into the array. And I also ran typical once performance runs using perf to record the number of instructions retired per cycle. So we can see generally, the better the performance, the more instructions per cycle we have. And and we can see that the FIFO 4 is retiring more than 2 instructions per cycle, and none of the other ones are even reach 1. Well, RigTorp does, but that goes a long way to explain why the FIFO 4A has such improved performance over 4, because, as I mentioned before, the AND operation is a single cycle. The remainder operation is 10, 20, 30 cycles or something. It kind of depends on the division being done. And I promised some references to good stuff. There they are, and that's my talk. Thank you. So, 10 minutes worth of questions. There's got to be at least one.
What was the size of the T that you're putting in your queue, right?
Great question. What was the size of the T that I was using? In all the examples, it was a signed 64-bit integer. So what I wanted to do was not test the performance of memcopy. Mm-hmm. So as well you know, it's a single instruction to move a 64-bit integer from one place in the processor to another place. So I think it's as close to measuring the performance of the FIFOs as you're going to get. You can expect, if you add larger memory data types, that the performance is going to decrease, and maybe drastically.
Right, just like when you're pulling data off your socket, you're probably pulling maybe 100.
Well,
like that sounded about right.
Yeah. Well, the thing is, right? A lot of times you can pull the data off the socket pretty darn fast, and you don't. If you're running a pipeline type of architecture like I showed there, you want to waste as few MIPS as possible on those FIFO operations, because they're giving you value, but not the same value as your computations are going to give you. So, does that answer your question? Yeah. Yes, sir.
Hello, Amir. The proxy optimization, it looks cool, but I wonder, did you verify that it actually does anything? Because like I've done similar benchmarking where I've had a chain of mem copies and I've put it into Godbolt, and the compiler is usually more than happy to turn mem copy A into B into C and just send it right to C. Like it's clever enough to usually optimize out redundant chains of mem copies. So did you check whether that actually does reduce the number of mem copies?
Not for this talk, but I have in previous engagements studied the code it's generated, and it used that. I mean, I came up with that optimization for that employer. Now, one of the differences was that the data was not stored on the heap. In that case, it was stored in shared memory. And there was another optimization that I wanted to put in this but my boss said it was too much, and based on the time it's left, I wouldn't have had time to talk with it. But from what I could, I'm not a great assembly reader, but from what I could tell, in every case it was mem copying into the shared memory, but the reads weren't necessarily mem copies. It was smart enough to know that was an actual object in there, and since I wasn't, mem copying it off into the distance, the smart pointer operations were converted into smart pointer operations into the core, in direct loads into the loads and stores into the shared memory. So I'm pretty sure it really does mem copy.
These cases seem to involve the kernel, maybe. So in and out of the kernel.
We use this same thing at work, and I don't think we at IEX for our trading engine, and I can't answer your question. I suspect that the mem copies actually happen, because you can see the SSE2 or AVX instructions being generated in the application code, and they're in the execution path.
Okay, thank you.
Yes, sir.
Great talk.
Thank you.
Why did the cached push and pop cursors have to be aligned to hardware interference size? Since they're not atomic?
That's a really great question. And the reason is that if these two threads are storing and loading values onto the same cache line, that data has to be transferred to the caches that serve other cores, because the value has to be, the value that gets stored has to be in one thread, has to be the value that gets loaded in the other thread. Otherwise, you can't make any reasoning. So by putting the values on separate cache lines, the loads and stores, the loads from the pop cursor, for example, don't interfere or require cache coherency. Those don't have to show up in the push thread when the push thread loads the push thread. Does that make sense? Go ahead and look up false sharing. I'd give you two references to look up. One is actually there's three. One is Wikipedia, the source of all knowledge. There's also, I think, another reference to false sharing in CP reference somewhere. And the third place to look it up is in the 1024's cores reference that was on slide 3 or 4. He has a whole page on he says it's not false sharing, it's real sharing, but everybody calls it false sharing. Yeah. That'll explain it far better than I can. I do know that I would probably bet you that almost all of that performance improvement is due to the removal of the false sharing, and a little bit of it, and a little bit of it is due to the relaxed atomic operations.
Okay, thank you.
That's as best as I can answer your question.
Thank you.
Thank you.
Hey, very good talk. Thank you.
Thank you.
So I think on the 505 example with reducing the mem copies through these
Yes.
RAI pusher and popper objects, one thing that is, I think, a little delicate and should be known is that it's hard for these to exist, for several pushers to exist at the same time on the stack, because they are FIFO in a sense, but their destruction will be in a last in, first out order, and obviously calling release on the first one and on the other will be tricky, and similarly for the pop operations.
So you're observing.
Yeah. So if I create a push and create another push before the first pusher got destroyed, then I think things can go wrong. But the single writer on its stack, like I create a push, want to push it, then do an if statement, call another push, then I close the braces. The closed braces will happen like in a last in, first out order, I think.
Oh, I see. Yeah, well, so DPDK does something like that. They have pushed multiple values on. They don't use the proxy thing, but they do manipulate cache cursor and real cursor to deal with multiple pushes and multiple pops. I've never had to do that yet, but it would be nice, I think, to have that feature. But it does complicate those pushers and poppers, I think, because you can't, if there's only space for 5, right, that's the maximum amount you can push before you have to go out of scope and increment the push cursor. And I don't know, it just seems, it was way too complicated for this kind of a talk. Thank you for your comment. Yes, sir.
Thank you for your talk. I really enjoyed it. In particular, thank you for putting on that one diagram the graphical icons with regard to acquire and release semantics. And in my experience, that's valuable because most people have trouble understanding that those two threads cannot make any assumptions about the start or the flow of time outside their own thread.
Exactly. That was something I was planning on talking about, that in my excitement to deliver the presentation, I skipped over.
And to that effect, when we talk about thread synchronization, we literally mean to sync, meaning the same thing, chronos, which is time. We're saying that these two threads can understand the same thing about the same moment in time. That's what we mean by thread synchronization. So thank you. That wasn't my question. My question is, I have a customer mandated requirement for a C++ 17 compiler. And so I don't have standard hardware destructive interference. Is there a workaround?
Yeah, just put 64 there.
Okay.
Yeah, so we have 14 seconds. Is that 14 seconds or is it over? The fact is, you can't use that in GCC 12 unless you put one of those, a flag in there that says, don't warn me if I use this. And the warning that you get when you use that variable, use that, that value explains why. And so in the GitHub code, I create this thing that's named that, but it doesn't have STD in front of it, and give it a value of 64 and make it a constant. But that's what I do. But what you will want to do, though, is as part of your unit testing, you're going to want to use sysconf. You're going to query sysconf or something to figure out what size your cache line is, and compare that to what the value that's being used. So what we do is we have a file that does all that. And a unit test on that file. So the file defines that it actually defines a variable called cache line size, assigns 64 to it, and then a unit test on that file validates that value, that 64, is the same that you get back from sysconf. You want that because not everybody's 64. Almost everybody's 64, but not everybody is. And I don't have a counterexample. Yeah. Right.
I was just about to mention in the larger system that you were describing, where you have sort of a, you're reading out of a socket and then pushing onto the queue. If you're, like we sort of touched on this with doing batch work. Like I think you're reading one value at a time, whereas you're going to be spending a bunch of time basically doing syscall work versus kind of grabbing a bunch of data in batch and then pushing it all at once.
Yeah. Well, that example reads a bunch of data. It reads. I didn't mention it, but the socket is a unicast or a multicast socket, so it'll read up to.
Okay, sorry.
Up to
I missed
MTU size,
it
and in our system, it's surprisingly enough somewhere around 1,400, but because of extra junk that gets added on. But I agree, it would be foolish to read 1 byte at a time and do it that way, but that's not what that code does. Thank you. Thanks, everybody.